What's up guys, it's me Sir Ernest, and today we're going to solve a problem involving damped oscillations. The problem reads, a simple pendulum consists of a mass m suspended from a fixed point by a weightless, extensionless rod of length L. Obtain the equation of motion, and in approximation that sine theta approximately equal to theta, show that the natural frequency is square root of g over L, where g is the gravitational field strength, and discuss the motion in the event that the motion takes place in viscous medium with retarding force 2m square root of gl. So we already solved the first part of the problem, wherein we want to know the equation of motion of a simple pendulum under the approximation of sine theta approximately equal to theta. Okay, so we know that when we solve our equation of motion, the equation of motion of a simple pendulum is theta double dot plus g over L sine theta equals 0. So this is the equation of motion of a simple pendulum. But this can be approximately equal to theta double dot plus g over L theta equals 0 if or for sine theta is approximately equal to theta. Okay, now this is what we call your small angle approximation. So therefore the solution to this problem is given by can be expressed as theta equals theta naught cosine omega naught t. Okay, where theta naught is the amplitude of the oscillation and omega naught is the angular frequency of your simple pendulum, which is equal to square root of g over L. Now, if there's a presence of a retarding damping force, okay, a linear damping force, when we say linear, that's linear in the angular direction. So that is equal to negative 2m square root of gl theta dot. Okay, so this is considered to be a one-dimensional because the retarding force is a function of one coordinate only. Okay, although of course in real life it's actually moving in 2 dimensions. Okay, so if this is the damping force, the equation of motion can now be determined by using Newton's laws as Fd plus the gravitational force along the s direction. So remember that if you have a simple pendulum like this is your mass, and this is your L, this is your theta. So this actually moves in a semicircle. So this direction is your S direction. So the force along that direction is FGS, which is equal to equal to mg negative mg sine theta, where mg direction is this one. Okay, so this is theta, so this FGS is also this one, this length. Okay, so FGS is equal to negative because the direction is in this direction. So this is negative mg sine theta. where this is FG, which is MG. Now, this is now equal to MS double dot. But we know that S is equal to R theta. So therefore, L theta. Because this is L. So this is L theta. And this is L theta dot. And this is L double dot equal S double dot equals L theta double dot. Okay. So FD is negative 2m square root of GL theta dot minus mg sine theta equals ml theta double dot. But for small oscillations, where sine theta is approximately equal to theta, we now have L L theta double dot plus 2 square root of GL theta dots plus G theta equals 0. So how did we arrive at this equation? So first is we cancel our masses because that's common, and then we rearrange the equation and equate it to 0. So from our definition of omega, remember that omega naught is square root of G over L. Okay, so if we're going to divide everything by L, we now have theta double dot plus 2 square root of G over L divided by L is square root of G over L. So this is 2 omega naught theta dot. And then G over L is omega naught squared. So this is plus omega naught squared theta dot equals 0. So from our previous discussion, this is actually has a very similar form as x double dot plus 2 beta x dot plus omega naught squared x equals 0. Okay, so in this case, your damping parameter is actually equal to your what? Is equal to your angular frequency. Good. So in this case, the angular velocity is equal to your damping parameter. So this is actually a case of a critical damping, where the solution to critical damping is equal to theta, which is a function of time, equals A plus BT e to the negative omega naught t. Now suppose we have initial conditions. So let's say our initial conditions are as follows. Let's say initially it was started at rest and it started at a certain angle theta naught, wherein theta naught is the amplitude. Okay, So from here, we can apply the initial conditions and we will arrive at the following result. We will arrive at your own time, you can do this already. A is equal to theta naught and P is equal to omega naught theta naught. You can refer to your notes later if you want, but this is the resulting values or expressions for your coefficients A and B. So therefore, the solution to this simple pendulum would be equal to theta naught plus omega naught theta naught t e to the negative omega naught t, or simply theta as a function of time equals theta naught times 1 plus omega t e to the negative omega naught theta omega naught t. And this is the final answer. This is the solution to the solution to the equation of motion of a simple pendulum under small angle approximation with a linear retarding force given by this expression. Okay, so in summary, the motion that took place or that takes place under this viscous medium, okay, would be a critical damping case. Okay, so that's it. I hope you learned something today, and I'll see you guys in the next video. Bye bye.